Hello class, it's Mr. Max here again. Today we're going to be learning about reactivity. We're going to show a fun example about just how reactive some things can be. And then we're also going to learn some definitions, some trends as we're looking at our periodic table. And then we're going to talk about some more examples by using our trends. So our first thing we're going to talk about, though, is a fun experiment that I have a video for, but our experiment is given rubidium and cesium mixed with water, what will happen? Do you guys think it would react? Water is what we drink every day. It's a really seemingly unreactive molecule, but if we put an alkali metal in there from our first group on the periodic table, how would it react? If you think it will react, which one will be the most aggressive reaction and why? So our rubidium's here, our cesium is here, so I was just curious, given these questions, what you guys think. So I encourage you to take a second to think about it, and then when you are ready, watch this video, which will be linked in our Google Classroom. Our next one that will be linked in our Google Classroom is this alkali metals video. This video shows some really good stuff about explaining why alkali metals and water are reactive. And I thought it was just a good way to explain something maybe in a different way than I would have. And it also gives you guys a chance to listen to someone else's voice than my own. So this will also be linked in our Google Classroom, so please pause this video to go watch this one and then come back. So what we're going to be talking about, though, in my video today is different words to help define our reactivity and talk about it. So let's taco about it. So ionization energy is abbreviated IE. Oops. It is the amount of energy it takes to remove an electron. So from different elements, it can be easier or harder to remove electrons, and this is the calculated measure of just how much energy it would take. Elements ionization energy increases as you go up and to the right on the periodic table, and a quick abbreviation for that is just our IE. Increases is this up arrow as you go up and to the right. So as always, I encourage you guys to write stuff that's underlined down. I think that's our most important takeaways from each lecture. So yeah, just a quick reminder. Our next word is electronegativity, which is abbreviated EN. It is our tendency to attract electrons, or an atom's tendency to attract electrons. And our element's electronegativity increases as we go up and to the right. And again, our quick little shorthand way of saying that is EN with an up arrow increases as you go up and to the right on the periodic table. So our reactivity is our tendency to undergo a chemical reaction. So if something is very reactive, it will very easily undergo a chemical reaction, and vice versa. If something is not reactive, it will take a lot for it to undergo a chemical reaction. So the more reactive, the easier it is to gain or to lose an electron or electrons. And our shorthand for this is just for metals. For this one, our metals have a different trend than our nonmetals, which we learned about where our nonmetals and metals are at last week. But our metals, our reactivity increases as we go down and to the left on the periodic table. And for our nonmetals, our reactivity increases as we go to the right and up on the periodic table. So the last thing we're going to talk about is our atomic radius, which is the size of the radius of the atom. So our radius, if we do not know what the word radius means, if we have a circle, such as a watch with hands, this hand that is the longest one going all the way to the outside of the circle is our radius. It will rotate all the way around, but it is also half of our diameter. So if you know what the diameter is, it's the line that goes from one edge of the circle to the other right through the center. So our radius is half of our diameter. and our atomic radius increases, so the size increases as you go down and to the left on our table. So I have another video for you guys I will link. It's just a short one, kind of showing the different tendency of reaction for different metals, and it also kind of shows what a reactive series of metals is. But for now, what I am going to talk about is what determines our reactivity, which is our valence electrons. Our valence electrons are what determines if something will react, how quickly it'll react, how aggressively it will react. So every element wants to be stable, and that means every element wants to have 8 electrons. So when we talked about our different groups, we talked about how our noble gases have 8 electrons and how they are very stable. Very, very stable. So different elements will bond to other elements to get to this 8 valence electrons. They will share electrons. They might take an electron from something else. They will do anything they can to find 8 and become stable. So when they do come together with another element, it is creating a compound, which we learned about earlier. And if we can remember, our definition of a compound is 2 or more elements chemically bound. So that's how this reactivity works. So the closer to the edge of the periodic table, the more reactive we are, except our noble gases. So our alkali metals on the far left and our halogens on the far right are both very reactive. Other things is we have some periodic trends that we were talking about. This is just another way to show it. There's a couple extra words in here we didn't learn about, but our electronegativity and an iron ionization energy is this, I believe, green color. So as we go to the right and go up, our ionization energy and our electronegativity increase. For our atomic radius, which we talked about, as we go down and to the left, this way, our atomic radius increases. We didn't talk about melting point or boiling point, but we talked about our reactivity. So our reactivity is different for our non-metals, which are off to the right up here, and our metals, which are over here. Our metals reactivity is increasing as we go to the left and down, and it is increasing for our non-metals as we go to the right and up. So let's work through some examples together. I think this was a great way to learn these elements. So if you guys can pause the video and ask yourself which element has a higher ionization energy, our fluorine or our carbon. So how would we find this answer? We would go back to our periodic table, which was on this slide before, and ask ourselves where fluorine is. So fluorine is up here and carbon is back here. And then we'd have to remember our trends. So our trend for electronegativity, we're talking about ionization energy, but it's the same trend, is increasing as we're going to the right and up. So if we look at carbon and fluorine is farther to the right than carbon, so it would have a higher ionization energy. Now, I would want you guys to do this one by pausing the video and thinking about it. So which element has a higher ionization energy, sodium or gold? So if we're looking at our table, sodium is in our alkali metals over here. Gold is down here. Looking at our trends, we have our farther to the right and farther up. So this one is a little tricky though, because our sodium's up here and our gold's over here. So we are lower on our periodic table, but we're also farther to the right. But since we're much farther to the right than we are lower, our gold has a higher ionization energy. All right, we have some more examples. So which element has a higher electronegativity, not ionization energy, but electronegativity? Chlorine or silicon? So if we're looking at our table, we can find chlorine right here. We can find silicon right here. So it's our same trend as we just had. Chlorine is farther to the right than silicon, so it would have a higher electronegativity. And then we have the same question for which has a higher electronegativity, potassium or calcium? So let's go find those on our table. We have potassium over here and calcium right next to it, more to the right. Calcium's farther to the right, so it would have a higher electronegativity. So some more examples. Now we're talking about our reactivity. So let's go back and remember our trend for our reactivity. For nonmetals, it increases as we go to the right and up. For metals, it increases as we go down and to the left. So going back to tin and strontium, we have to go find those on our table. So tin, I believe, is right here, and strontium is over here. So for our reactivity of metals, these are both metals in our metal section of our table. Our reactivity is higher if we're to the left and farther down. So they're in the same row, but strontium is farther left, so strontium is our answer. Which element is more reactive between our oxygen and our selenium? So we got to find them. Our oxygen's here, our selenium is just below it. And for our nonmetals, our reactivity was higher as we went to the right and up the table. Oxygen is higher up, so oxygen is more reactive. Then our next question is, which element has a larger atomic radius, sodium or neon? So we have to remember our trend for atomic radius, which is the atomic radius gets larger as we go to the left and down on the periodic table, and between sodium and neon. So we have to find sodium, which is over here, and neon, which is up here. So sodium is both farther left and lower on our table, so it would have a larger atomic radius. And then our last one is, which element has a larger atomic radius between gallium or chromium? So gallium we have to find, and chromium. Gallium is here, chromium is here. Chromium is farther to the left, so it has a larger atomic radius. And that is all we have for today. I will make sure I post those videos that are in the presentation in links for them in the Google Classroom, and be very clear like which one to watch first. It works best to pause the video in the middle of this presentation, pull up that link, watch it, and then continue this one. But however you would like to do it, if you want to watch those videos multiple times, I encourage you to do so as well. So thank you guys for your attention, and I hope you have a great rest of your day.